Okay, in this lecture we're going to take a look at cubic functions. Just a quick introduction. So how do we recognize a cubic function? So essentially cubed is the highest power. So cubed is the number 3. So a cubed, that's a cubic function there. So just some examples. Here's our variable, highest power is cubed. So all of these are varying examples of cubic functions. The first 3 are simple because there's only one term on the input side. So these are all proportional, as in when the input is 0, the output is 0. The bottom one then is a polynomial. Simplest cubic equation looks like this, and this is a polynomial then. It's the general cubic way. You come across this one more when you're dealing kind of in maths. When you're dealing with the real world, thankfully, they tend to be a little bit more simple. So like quadratic and linear functions, cubics also have some similar properties. For every input value, a single output value exists. This produces a continuous line on a graph. So in other words, the line is never broken. And then the shape of the curve is determined by a number of factors, but one thing is it'll never have more than 2 turning points. Sometimes it'll only have 1 turning point of inflection it's called, but it will never have, so it'll have somewhere between 1 and 2 turning points. We'll talk about the different curves now. So if we've only got a simple function with one input term, like this, then our curve looks like this, and there's only one point of interest, one turning point. It's actually called a point of inflection. We'll come across these later on. And that's the typical curve there. If there are 2 or more input terms, polynomial, then we get this type of a curve. It looks a bit like a chicane on a racing course. So most of the functions we'll examine in this module are simple. So these only have one term on the input side. So these are all typical cubic functions. Very often S will be A as well if we're talking about a cube, as we'll see. Even though this looks like a complicated function, there's still only one term, but there's 3 input values. So we'll talk about those a little bit in this lecture and in more detail on the next lecture. So all of these functions have this type of a graph. Now in real life, we usually don't see the negative side. There's no such thing as a negative input. So usually a cubic curve looks like this when you meet it in real life, with positive numbers for the x value, be it t, be it length, be it whatever, and positive numbers here. So we only see this bit of the graph. And as we'll see on the next slide, that can be sometimes a little bit confusing if you've only got a graph, because a quadratic function also looks the same. These are what we met last week. And in a couple of weeks' time, we'll meet exponential functions, and they produce a similar looking curve as well, even though it's a completely different function than a cubic function. So both of these functions, you'll agree, are completely different than our cubic function. And these are some examples of exponential growth. So how do we know if data is cubic? So say we've gathered this data here. Note my values just go from 12 up to 22. Those are my x values. And I've done this experiment and these are my measurements. Well, we could just draw a graph. And it's going to look something like this. There's my x. There's my y. But as I said, that's not conclusive. We don't know if it's cubic or quadratic or exponential. So what we can do though is instead of the x values, we can cube all those x values. So remember I said I went from 12 up to 22. We're going to actually cube all the x values. And now you can see there's a nice relationship. There's actually a linear relationship between the two. If we now plot x cubed versus x, those x cubed values, versus y, then we'll get a straight line. And if you get a straight line when you do that, when you plot this and you get a straight line, you can now say y is proportional to x cubed. So you know definitively that whatever data produce this graph is cubic in nature. Now, I'm only introducing this idea here. We're not going to explore it any further at the moment. But towards the end of the module, we will certainly be exploring this concept in quite a bit of detail. I'm just introducing it now. So we'll push on. So if we take a look at a 6-inch diameter ball, remember we looked at a 6-inch diameter pizza last week, and we doubled its size, we doubled the diameter, or doubled its radius is another way of looking at it. So in this case the radius would be 3, and here the radius is 6. If we work out the volumes, just taking the radius of 3, and keeping the value pi rather than turning it into a number, we can see the volume of this sphere, the 6-inch sphere, is 36 pi. Now if we double that input, so we've doubled the radius, but note it's been cubed. So when we work this out, it's 8 times greater. So the 12-inch diameter ball has 8 times the volume of the 6-inch diameter ball. And as we'll see, this obviously has very big consequences for just real life activities. So in a proportional cubic function, if the input is doubled, the output is multiplied by a factor of 8. So we'll just take a look at some simple cubics. Here we have a cube, and here we have a sphere, like I was saying. So these are just some examples of kind of cubic functions in real life. So the most obvious one, and the one I've been dealing with to date, is volume. Any simple shape's volume is governed by a cubic function of some nature, and the units always reflect this. Centimeters cubed, meters cubed, feet cubed, whatever we're talking about. Oh. Now another one, I introduced this function but didn't talk about it, is power and wind speed have a cubic relationship. So here I'll talk about this example in the next lecture in a lot more detail. But here we have a wind speed of 10 meters a second. And if we move the turbine to the top of the hill so that the wind speed is doubled to 20 meters per second, this turbine here will produce 8 times the power of this one here. So if this one produces 1 kilowatt per hour, this one here would produce 8 kilowatts per hour. In other words, 8 times the revenue. It would earn 8 times the money of this turbine here, which seems incredible, but that's the nature of cubic functions. Another example which we'll explore in more detail in the next lecture is pumps and fans. So if you speed up a fan or a pump, anything that's moving air or water or liquid, the power used and the speed of the pump have a cubic relationship. So again, if you're, say, in a kitchen and you double the speed of an extractor fan, if you're in a commercial kitchen and it's feeling a bit hot and you double the speed of the fan, your electricity bill will increase by a factor of 8. And similar with fans, so they all move with this centrifugal action. So a centrifugal pump and fan will have this cubic relationship. And just, guys, why this is so important is approximately 20% of the total energy used on the planet. So we're talking for transport, for heat, for generating electricity. 20% of that energy, total primary energy requirement, is used by pumps and fans. And you never really hear it been talked about in the climate change discussions, but they use a huge amount of power. So that actually brings us pretty much to the end of this one. I said it would be a short one, and it is. So I'll finish up there, guys, and in the next lecture then we will develop some of these concepts in a lot more detail when we start to analyze cubic functions. So thanks again for listening, and we'll chat to you soon.